Hey everyone, and welcome to This Explainer. I am absolutely thrilled you're here. Today, we're going to do something truly fascinating. We are pulling back the curtain on those massive AI data centers you're always hearing about to see exactly how a single word or token is generated by a GPU. If you've ever been curious about the actual physical mechanics that make artificial intelligence possible, well, you are in the exact right place.
So, it's a pretty simple premise, right? You type a question into a prompt box, you hit enter, and almost instantly you get this impossibly smart answer. Now, we all know that ChatGPT and other large language models run on fast clusters of computers somewhere up in the cloud. But today, we're zooming way down, to the micro level. We're asking the most fundamental question: what is the actual hardware doing in those tiny fractions of a second right after you hit enter?
To really understand AI, we actually have to look backwards for just a moment. Surprisingly enough, the very chips powering the AI revolution, graphics processing units or GPUs, weren't originally designed for artificial intelligence at all. They were actually built for rendering 3D graphics in video games. Think about a game screen for a second. It has millions of pixels, and to render a 3D model, the computer has to calculate the lighting, the position, and the color for every single one of those pixels at the exact same time. It required millions of simple calculations done all at once. And as it turns out, that exact kind of parallel math is exactly what modern AI models desperately need.
Okay, so here is our highly structured roadmap for today. First, why GPUs for AI? Second, the CPU versus GPU matchup. Third, inside the GPU architecture. Fourth, the token's journey. Fifth, from chip to supercomputer. And finally, number 6, the true face of AI.
Let's dive right into Section 1. Why GPUs for AI? The math behind the magic. When you interact with a large language model, it can really feel like you're talking to a thinking, breathing entity. But fundamentally, AI models contain billions, sometimes even hundreds of billions of parameters. And to use those parameters, the GPU isn't executing complex, human-like logic. Not at all. It's actually doing something much more repetitive. It is performing massive, rapid matrix multiplication. We are talking about multiplying gigantic grids of numbers together in unbelievably short amounts of time. Moving right along to Section 2, the CPU versus GPU matchup. Engineer versus factory. To truly grasp this, think of a standard CPU, a central processing unit, as a brilliant, highly educated engineer. Now, this engineer is incredible at handling complex logic sequentially, figuring out difficult if this then that branching paths, and basically controlling the entire system. But they work on tasks one by one. The GPU, on the other hand, it's like a massive factory employing a million workers. These workers might not have PhDs in system logic, but if you hand them a million simple mathematical equations to solve, they will execute all of them simultaneously. This is the magic of parallel computing, and it's the absolute core advantage that makes AI possible. Which brings us to Section 3, inside the GPU architecture. Let's step onto that microfactory floor. First up on the floor is the Tensor Core. This is a genuinely revolutionary piece of hardware built directly into modern GPUs. Unlike your general processing cores, Tensor Cores are designed with one singular obsessive purpose: to just blast through matrix multiplication. By dedicating actual silicon specifically to this one task, GPUs provide the staggering raw compute performance that deep learning and massive neural networks demand. But look, hardware is pretty much useless without instructions, right? So, to orchestrate this massive factory, developers use something called CUDA. Think of CUDA as the master translation layer. It links high-level AI frameworks like PyTorch directly down to the physical hardware. This means programmers can build incredibly complex AI models using simple software languages, and CUDA just translates all of that into instructions for the millions of workers on the GPU floor. And the best part? No one has to manually wire individual transistors to make it happen. But here's the catch. Having super fast workers reveals a massive bottleneck. Imagine those lightning-fast tensor cores finishing their math in a microsecond, but then having to just sit there and wait for the next batch of numbers to arrive over a slow connection. The GPU would just sit idle. Compute, wait. Compute, wait. In the high-stakes world of massive data centers, an idle GPU means precious processing power, and literally millions of dollars is completely wasted.
Enter HBM, or high bandwidth memory. Going back to our factory analogy for a sec, if a standard computer's memory connection is a narrow, single-lane dirt road, HBM is a massive multi-lane superhighway.
It is incredibly fast memory stacked directly alongside the processing cores. This guarantees that the raw materials, the data, keep flowing instantly to the computational workers, making absolutely sure the tensor cores never have to stop and wait. And this really illustrates the entire physical design philosophy of the modern AI chip. The whole architecture revolves around keeping massive amounts of AI model weights, the actual data that makes the AI smart, stored right there in that high bandwidth memory next to the compute cores. It's all about proximity. The shorter the physical distance the data has to travel, the faster the matrix math can be completed.
Okay, let's switch gears a bit. Section 4, the tokens journey, from text to vectors.
When you ask an AI a question, the system absolutely does not send English text to the GPU. The GPU wouldn't have a clue what to do with words. Instead, the software first passes your text through a tokenizer, which essentially chops it up into smaller pieces. Then it converts those pieces into token IDs, which are just numbers, and finally embeds them into vectors. This is a crucial transformation. It turns human language into pure multidimensional math. Only then does the GPU get to work.
Once converted into math, these vectors enter the neural network, specifically the transformer architecture. They pass layer by layer right through the model. Inside, an attention mechanism calculates the really intricate relationships and context between the different tokens. Like, how does the word bank relate to river versus money? The attention mechanism figures this out, and it's all powered by that continuous, massive GPU matrix multiplication across those tensor cores we talked about earlier.
All right, zooming out now to Section 5, from chip to supercomputer, scaling AI hardware.
Here's the thing. When an AI model completely outgrows a single chip, we have to scale up, big time. We take multiple GPUs and connect them inside a single server using lightning-fast networking. Then, we connect racks and racks of those servers together to form a massive cluster. Ultimately, we network thousands of those clusters to create entire distributed AI data centers. Basically, we're building a massive, unified supercomputer out of thousands of individual graphics chips. Now, what are these giant, warehouse-sized supercomputers actually doing all day? It basically breaks down into two phases. Most of these massive infrastructure clusters are used for training. This is where the model is fed vast amounts of internet data over months to learn and continuously update its billions of parameters. However, the actual interaction you experience when you open ChatGPT on your phone, that's called inference. This requires much less compute. During inference, the GPU simply uses those already learned parameters to calculate predictions based on your specific prompt.
And that leads us perfectly into Section 6, the true face of AI, the illusion of intelligence.
You've probably noticed that ChatGPT types its answers out word by word, almost as if it's thinking in real time. Well, that's not just for dramatic effect. It's a direct reflection of how the hardware works. It's called autoregressive token generation. The model analyzes your prompt, predicts the most probable next token, and spits it out. Then, it takes that brand new word, adds it back to your original prompt, and runs the entire massive mathematical calculation all over again just to predict the next word. Inference is just this highly repetitive, continuous loop.
So, to really conclude our unmasking of the AI illusion here, we have to accept a pretty fascinating truth. The GPU has absolutely zero understanding of English, coding, or poetry. None. The AI model simply defines what mathematical equations need to be solved, and the GPU executes them at blinding, unfathomable speeds. It's a total miracle of statistical prediction, but it's not conscious comprehension.
When you take a step back and look at the sheer scale of this whole process, it is literally staggering. Generating just one single sentence from an AI represents hundreds of millions, sometimes billions of matrix multiplications. Data is constantly flying from that high bandwidth memory into the tensor cores and back again. This staggering requirement for pure, raw computational muscle is exactly why tech giants are in a desperate, multi-billion-dollar race to build out massive AI data centers. The math simply demands the hardware. I want to leave you with a final thought to ponder today. When you read a beautifully written paragraph by an AI, it feels creative, it feels deeply smart. But if that intelligence can be entirely synthesized by high-speed parallel math humming away inside a silicon microfactory, where exactly does the mechanical illusion end and true intelligence begin? Thank you so much for joining me on this explainer. Keep asking great questions, and I'll see you next time.